Welcome to Visual Algebra Lecture 5.3, Two Theorems on Orbits. If a group G acts on a set S, then the larger the stabilizer is of a particular set element, the smaller the orbit should be, because there are fewer group elements to move it. This qualitative observation can be made precise via a hallmark result called the orbit stabilizer theorem. This is a more general case of something that we saw back in Chapter 3. That the size of a conjugacy class, that is an orbit, is equal to the index of the normalizer or the centralizer, that's the stabilizer, depending on whether we're conjugating subgroups or elements. That's our first theorem on orbits. For the second, consider the dual definition of stabilizer, which is the fixator of a group element, little g, defined as the set elements that little g fixes. The larger these fixators tend to be, the more fragmented the action graph should be, and thus the more orbits one should expect. The orbit counting theorem makes this qualitative observation precise. In this lecture, we will state and prove both of these, and then we'll include some nifty visuals to give you some intuition. I think you're really going to like these. So let's get started. Let's start by revisiting our favorite example of the dihedral group D4 acting on our set of 7 binary squares. Here's the action graph. Pressing the R button just rotates everything 90 degrees counterclockwise, and the F button flips things about the vertical axis. So our first qualitative observation is that elements in larger orbits tend to have smaller stabilizers, and vice versa. And let's think about why that makes sense. So if you're in a small orbit, then there's going to be a whole bunch of paths, or 8 different paths, but there's not many destinations. So here, every path has to start and end up here. And then here, if you just close your eyes and pick a random destination, it seems like half of the paths will end up where they started and half of them will end up over here. And over here, there's 4 possible destinations. So out of the 8 possible elements, it seems like that you should expect, on average, about 1/4 of the paths from one element to end up back at that element. And we can actually quantify that. But just qualitatively for now, elements in larger orbits tend to have smaller stabilizers, and vice versa. Our second qualitative observation is that the more check marks an action table has, the more orbits the action tends to have. And remember that in an action table, we put the group elements along the columns and the set elements along the rows, and there's a check mark in the GS entry if pressing the G button fixes the S state. So if an action table has a lot of check marks, that means if we start at a random element, there's a larger probability that pressing a button is going to just fix it. And then the fewer check marks, if there's not very many check marks, that means if we start somewhere and we press a button, we're more likely to move, to go somewhere else. That is going to cause the orbits to merge. Whereas if we have lots of check marks, that's going to cause the orbits to be fragmented, and there should be more of them. Let's summarize our 2 qualitative observations. First, elements in larger orbits tend to have smaller stabilizers, and vice versa. Second, action tables with more check marks tend to have more orbits, or the actions have more orbits. Recall that the check marks correspond to the fixators. So when an action table has more check marks, that just means that the fixators are larger. So the group elements fix more things, and so there should be more orbits, and vice versa. Both of these qualitative observations can be formalized into quantitative theorems. The first theorem is called the orbit stabilizer theorem. It says the size of an orbit is equal to the index of the stabilizer of an element in it. Next, the orbit counting theorem says that the number of orbits is equal to the average number of things fixed by a group element. You can think of that as the average number of check marks in a random row, or equivalently the average size of a fixator of a random group element. if we set up our group actions correctly, the orbit stabilizer theorem will imply two results that we've already seen. First, the size of the conjugacy class of a subgroup is the index of the normalizer of that subgroup. And secondly, the size of the conjugacy class of an element is the index of the centralizer of that element. And I say it implies this because if we set up our group actions correctly, the conjugacy classes will be the orbits, and the normalizer and the centralizer will be the stabilizer. We can also determine the number of conjugacy classes of subgroups or elements from the orbit counting theorem. That's a result that we have not yet seen before. Let's start with the orbit stabilizer theorem. Formally, if we have a group action phi from a group to the permutations of a set, then if we take any element S in the set, the size of the orbit containing S is equal to the index of the stabilizer. Now, by Lagrange's theorem, recall what Lagrange's theorem says, that's just the index of H in G is the size of G over the size of H. We can rewrite this as the size of the orbit times the size of the stabilizer equals the size of the group itself. Because remember, this is just the size of G over the size of the stabilizer. Now, Lagrange's theorem assumes that G is a finite group, although it really works for infinite groups as well. It's just not interesting because if G is infinite, then the right-hand side is infinity and the left-hand side, one of these things has to be infinity. So I prefer this form because it's more meaningful for infinite groups, but also because it suggests how the proof is going to go. So the proof goes by constructing a bijection between the elements in the orbit and the cosets of the stabilizer. So this is more indicative of the intuition behind it than what this is. Here's a picture for what the orbit stabilizer theorem is really saying, but also it's an outline for how the proof is going to go. If you've been watching my video lectures up until here, you've seen a picture just like this in several lectures in Chapter 3. I encourage you to check out my lecture on centralizers if you have not seen this, because in there I give an analogous picture for relating the cosets of the centralizer and the size of the conjugacy class of an element, but I also recap the analogous one for cosets of the normalizer and conjugacy classes of the subgroups. So we have an element S that we picked, and let's let H be the stabilizer. That's a subgroup, and that means that every element in the stabilizer, by definition, let's call one of these things a little h, fixes S. So that means that S is equal to S dot phi of H for every single thing in here. And then H will have cosets. H could be normal. It could be fully unnormal, meaning that all the other cosets could be blue or they could all be red. I'm just going to pick a couple of them and say this one's red and this one's blue. But the idea is that everything in this coset will send S to the same destination. So if we have some other element in this coset, let's say it's A prime, then by definition of what the coset means, this is H times A for some element H in H. So when we start with S and we press the H button and then the A button, well, the H does nothing, so we just get whatever A does, and well, that's in the same coset, so pressing the A prime button is the same as pressing the A button. Okay, so going back here, how many cosets do we have? That by definition is the index of the stabilizer. And how many destinations do we have? That by definition is the size of the orbit. So the proof of the orbit stabilizer theorem really is to just construct this map from a coset to a destination. You can see how it's going to be. Phi of, I don't want to call it phi because I'm using phi up here. Let's call it f of HA gets sent to S dot phi of A, and show that this map is well defined because it depends on a coset, so it doesn't depend on which element we take, that it's one-to-one, and that it's onto. Be careful, you do not want to prove this is a homomorphism because neither this set of cosets or this set of elements are actually groups. Let's now understand the orbit stabilizer theorem in terms of action graphs and our familiar example. So once again, we want to exhibit a bijection between elements in the orbit and right cosets. So here's our group switchboard. Here's that size 4 orbit of our binary square example. And here are the cosets of the stabilizer. So if we call this element S, and then the stabilizer, let's call it H. Again, here are the cosets, but let's think about why this makes sense. So all of the paths that start and end here are going to either be of the group element 1 or F. That's what the stabilizer is. So how do we get from here to here? Well, we have to, we can first do any path we want that starts and ends up here. So we can do F, we can do the identity, we can do R to the 4th, we can do RFR, which is equal to F, but doesn't matter. As long as we do a loop here, we're in the stabilizer, and then we have to do R. As long as we do that, then we will end up here. Now, HR is R and FR. I mean, there's actually one more we could do. I said R, we could do FR, but that's going to get us here nonetheless. How do we go from here to here? Well, we start by doing any loop that we want, in other words, something in the stabilizer, and then we do R squared. We've just described all the elements in HR squared. And then to get from here to here, we do any sort of loop that we want, and then we do R cubed. I just described the right coset H R cubed. So this bijection is going to send the right cosets in the stabilizer to, or I guess here, to elements in the orbit. And you can see how that, let me write what I did last time on the previous slide. We're going to send HA to S dot phi of A. So this element is S dot phi of R. This element is S dot phi of R squared. This element is S dot phi of R cubed. And this element is S dot phi of the identity. Now it's time to finally prove the orbit stabilizer theorem. I'm going to introduce some new notation for this chapter, and that is the following. If I write H with a \G, that's going to denote the set of right cosets of H in G. Recall that in the previous two chapters, we let G/H, we said G mod H, to be the set of left cosets. Because in chapters 3 and 4, the only time that we ever considered a set of cosets is when the subgroup was normal and we had a quotient, so the left cosets and the right cosets were the same. So that's not going to be the case in this chapter, so we have to distinguish between these two. Okay, it's time to prove this. Let's let H denote the stabilizer of S, and let's define a map. I'm going to call it F, because phi is taken, from the right cosets of H to the orbit containing S. And I have to tell you how we're going to define that map. So F sends a coset HG to the set element we get by pressing the G button from S. So S dot phi of G. So we first have to show that this is well defined, because our definition involves a coset, and that could have multiple representatives. So for this, let's suppose that we have two cosets that are actually the same. HA equals HB, say. Okay, then what does that mean? Then, well, we can move the B over and we can write H A B inverse equals H, right? So let me put this implication here. Well, then what else can we do? Well, by our boring but useful coset lemma, we can say that this means that A B inverse is in the stabilizer H. Because again, if H times some element X equals H, that means that X had to be inside of H. So this is by our boring but useful coset lemma. So that is Hx equals H if and only if X is in H. Now, what next? Well, this being in H means that A B inverse is in the stabilizer. So that means that S dot phi of A B inverse equals S, and this is just the definition of the stabilizer. And now we can just use properties of homomorphisms. So I'm going to write S dot phi of A times phi of B inverse. Are you okay with me doing two things at once? I split this apart and then I pull the negative sign outside. Well, equals S, I have to be careful. And then I can just move this element to the right-hand side. I can write, say this is the same thing as, or this implies S dot phi of A equals S dot phi of B. And now that's what this function was. So that just means that F of HA equals F of HB. And that's what it means to be well-defined. If we have two inputs that are actually the same, then the function has to be the same on both of them. Okay, so our function is well-defined, and now we just have to show it's a bijection. So why is it 1, 2, 1? So to show that it's 1 to 1, we have to suppose that we have two inputs that get mapped to the same output. So suppose that F of HA equals F of HB, and we have to conclude that HA equals HB. And remember how sometimes well-defined and 1 to 1 are often dual properties? So we can, if we have one of them, we can just get the other. So indeed, if the outputs are the same, if F of HA equals F of HB, that means that S dot phi A equals S dot phi B. That's what this means. So that means I can reverse this. I can make this arrow double-sided. And then this, if we have this, we can move the phi of B over to get this. So indeed, I can make this arrow double-sided. And that just means that I can move the B inverse inside here and get this. And now that's what it means for a B inverse to be in the stabilizer. And well, that means we can reverse this arrow, and then we can basically just reverse every single arrow. These implications are really if and only ifs, each one of them, and then we conclude this. So for 1 to 1, let's just say change each right arrow into double right arrows. And then what about 1 to 1? Or sorry, onto. Well, onto is straightforward because if I give you something on the right-hand side, you can tell me what gets mapped to it. If I give you, so let's write this up formally. Let's take S prime in the orbit, which by definition means it's S dot some phi of G in the orbit of S. Well, then we have a preimage. Then F of HG equals S prime by definition, and that's what it means to be onto. So that's the end of the proof. Now remember, we do not want to show this is a homomorphism. I see that mistake sometimes. People try to do like F of HA times HB equals, and they can kind of fake it notationally, but it doesn't make any sense because neither of these things necessarily have a group structure. So this is the proof for right actions. If the proof for a left action is analogous, I encourage you to try that. You can basically just hold the proof of this in the mirror, but it works flawlessly. And that's a good exercise because then you're doing something that's a little bit different, so you have to kind of work out the details on your own rather than just copy this thing line for line. So give that a shot. Even if you understand this, you really have to do some of these for practice before you can do actual problems like on exams. Now we come to our second theorem on orbits, called the orbit counting theorem. So our first theorem, the orbit stabilizer theorem, involved the size of the stabilizer of an element. So remember, if we have a set element, then the stabilizer, you just look at that column and look at the group elements where there is a check mark. That's the stabilizer. And the larger the stabilizer is, the smaller the corresponding orbit is. Now this theorem, orbit counting theorem, is going to involve the number of check marks in rows. And remember, these are the fixators. So the fixator of R squared are the 3 set elements where there are check marks. So the orbit counting theorem says if we have a finite group G acting on a set via homomorphism phi, then the number of orbits is, what is this saying? So we are adding up the size of a fixator for every group element. So that means for every group element, every row, we count the number of check marks and we add those up. So this is just the number of check marks in the table. And then we just divide that by the size of the group, which is the number of rows. So the right-hand side here is just the average number of check marks per row. And the idea is that is the number of orbits. So in this example, we have, 7 check marks in this row, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, 2, 3, 4. So we have 24 check marks for 8 rows. That's an average number equal to 3. And we saw that there are 3 orbits in our running example of binary squares. Now this is called the orbit counting theorem, but I will say that some books call this Burnside's lemma, which is a terrible name for multiple reasons. One is it not really indicative of what it means, but also it's not due to Burnside. It's, I think, due to Frobenius. So some books call this the lemma not due to Burnside, which is, I don't know if that's a better or worse name. At least it's honest about it. But the orbit, just call it the orbit counting theorem because that's what it is. Before we prove this, I want to say a few words about how the proof is going to go, because it looks messier notationally than it should. This is one of those ones where there's a double sum in it and a bunch of equalities, and if you look at the slide on my website or the proof in Wikipedia or a textbook, it's a little daunting. And you can work your way through each of the equalities and convince yourself that it works, but the concepts are really not that bad. So here's how it's going to go. We're going to take this sum right here, which is just the total number of check marks in the orbit table. And here we're adding those up row by row. Of course, we could add them up column by column instead. So that's what we're going to do. We're going to take this sum and do it by columns. In other words, we will write this as 1 over the size of the group times the size of each stabilizer. And then this thing here is just begging for us to use the orbit stabilizer theorem. And that's just the size of G divided by the size of the orbit of S. So remember, the size of G equals the size of the orbit times the size of the stabilizer. So we're going to plug this thing in, and then we're going to go from there. Here is typed up what I just wrote down. If we take the total number of check marks in the orbit table, I'm going to forget about the 1 over the size of the group now and just look at this. That is, by definition, the set of ordered pairs g comma s in the orbit table where s dot phi of g equals s, but we can also count by columns. And again, it's a lot of proofs in textbooks or Wikipedia are going to have this equality without this intermediate step or without any picture of the orbit table. And the orbit table really makes it clear why these things are the same. Okay, so let's remember the orbit stabilizer theorem. So the orbit stabilizer theorem says that the size of G equals the size of the orbit of S times the size of the stabilizer of S. So this is what we want to replace. So we can replace that with the size of G divided by the size of the orbit. So this is by the orbit stabilizer theorem. This is equal to, we're adding up for all elements in the set, the size of G divided by the size of the orbit. And of course, we can pull the size of the G right out because it does not depend on the sum. And so what we're doing now is taking the size of G times over all set elements, little s, 1 divided by the size of the orbit of S. Okay, so now what? Well, here's where I'm going to draw a sample action graph so you can see why this is not as bad as it seems. And I'm going to do the same example that we've been seeing so far, which is our binary square example. So it doesn't have to be exact, but why not? Let's do it. So there's one orbit. Then there's another orbit, which looks like this. And then there's another orbit that is, I can move it down here a little bit, where it is a fixed point. So here are the actual set elements. And let's think about what this is saying. So we are, for every element in the entire set, we're going to ask that element, what proportion of the orbit are you? 1 divided by the size of the orbit. So if we go over here and we say, okay, this is S, or this is S. What is 1 divided by the size of the orbit? That's equal to 1/4, right? So for every, so let me write that. I'll use green here. So this set element is 1/4 of the orbit. Again, that's what we are putting right here. This, of course, is also 1/4. 1 divided by the size, the entire orbit is size 4. 1/4, and this here is 1/4. We go here and we say, okay, 1 divided by the size of the orbit is 1/2. So that's 1/2, and this is 1/2, and over here this is 1/2. Sorry, this is not 1/2. There's one element here, and 1 divided by the size of the orbit is 1. So this contributes 1. So this sum here is just the sum of all of these little individual numbers. And do you see why that is the number of orbits? So what is the sum? 1 plus 1/2 plus 1/2 plus 1/4 plus 1/4 plus 1/4 plus 1/4. So of course what we're doing is we're just adding up the number of orbits. So that's basically the proof, but again, we have to formalize this. So I'm going to write this as, so the size of G, but this thing, let me use a different color so I can distinguish it. So the size of G, and then I'm going to, instead of adding this up for the entire set, let's partition it by orbits. So let's add them up orbit by orbit. So this sum, so let's take for each orbit in the set of the orbits, we will take the individual element, little s, and 1 over the size of the orbit of S. So again, we're doing the same thing, but instead of just adding up, I'm forgetting a parentheses, instead of adding them up individually, element by element here, we're doing it orbit by orbit. So let's do one orbit at a time and then add those up. So this is just equal to that. And this inner sum here, again, for each orbit, we're taking 1 divided by the size of the orbit for every element in the orbit, this here is just equal to 1. And again, that's the sum over each orbit is equal to 1. So this whole thing just reduces down to the size of G times, we're going to add up for every orbit, we're just going to add 1. And that is the size of G times the number of orbits. So this number of orbits is just the size of the set of orbits. And now if you think about what we have, we take what we started with, which is equal to this, and we equate these two things. And that is the orbit counting theorem. In other words, we just divide both, we move this size of G over to here and make it 1 over the size of G, we get exactly what we wanted to. So if you see this proof purely algebraically with these sums and without a picture like this, an explanation for like why this is equal to 1, and also without a fixed point table, that was key of like counting by rows and counting by columns to understand what this is really saying, then it just becomes, this notational, I don't want to say nightmare, but it's more of an exercise in notation rather than intuition. And that's a theme in a lot of the stuff that we're going to do in this chapter. Group actions is something that is a lot of students say they don't really understand. I've heard graduate students say that they never really got it. Ones who go on to an area not in algebra. I've heard faculty members say that they never understood it in grad school. There's things in grad school I never really understood that are not in my area. And a lot of this is because if it's not taught visually, if it's not taught with these analogies, it's, if you don't quite get it, you can move on and just not get it. So what we're going to do next in the next lecture is we're going to look at a number of actual group actions involving a group by multiplication on its elements, by conjugating its elements, by conjugating its subgroups, and by multiplying cosets. And for each of those actions, we will interpret our 5 fundamental features, and we will interpret the orbit counting theorem and the orbit stabilizer theorem. And in some cases, we'll get new theorems that we had not seen before. And in other cases, we will get intuition. So it's a really good exercise now that we've seen our 5 features and we've seen these 2 big theorems on orbits to do a bunch of examples. And I think that's really going to solidify this going forward. So you're not going to want to miss this next lecture. I'll see you then.